Hello there, and welcome to part 4 of Machine Learning Basics. We've already covered up to this point linear regression and logistic regression, as well as optimization in terms of gradient descent. And now we're going to talk about a concept that you really need to consider when you're choosing your machine learning model, and that is variance versus bias trade-off. So in this section, we're going to talk a little bit about what we mean by that. And so without further ado, let's head over and start this portion. Okay, Control L, I'm going to get my laser pointer. So we talked again about these different concepts, and here we're going to cover variance versus bias trade-off. And then in the last part of this, we're going to talk about regularization, which is really, one of the knobs that we have for controlling this model variance and model bias, which are these two opposing concepts that we really need to consider when we're training a machine learning model. Okay, here's a few of our true-false test questions. The first one is high model variance is associated with high variance in the features. This is false. So while it sounds like it could be true, when you're talking about variance in the model and at high variance, it's really about high variance in the outputs. So again, how drastically the outputs change, with your model. And for the second one, with respect to the variance versus bias trade-off, using a model with less bias is better than a model with more bias. Again, this is really about the definition of bias. And so in the context of variance versus bias trade-off, bias is referring to how well does your model capture the training data. And just because it can have a very low bias does not necessarily mean that you have a better model. In some cases, where we'll show what overfitting is, you can have a model that very accurately captures the training data, but then you feed it new data, new test data, and it does very poorly. And so this is what's called overfitting, and we'll talk a little bit about that here as well. Here's just conceptually what's going on. You can think of the x-axis as different models, and so, along any number of different dimensions, there's a lot of different knobs that you have in terms of like setting up and tuning your model. And what happens is, as you move along with different, let's say just model complexity, for instance, as you increase model complexity along the x-axis, your bias is changing. It's getting lower and lower, which means your model complexity is leading to you better capturing the training data. However, this variance term is actually increasing. So it means there's more variance in your outputs, and you're actually starting to do worse with capturing new data. And so this signals a shift between you have an underfitting regime where your model is too simple, for instance, and an overfitting regime where your model is too complex. And there's some optimal middle ground. And that's really where you want to shoot for with your machine learning model in order to capture, really the best of both of these, the bias and the variance. Okay, to illustrate, let's go back to this shot data set, where again, we have thickness as an X or an input, and then the metric V50 is on the Y-axis. Within this plot, again, these red data points are our actual data points. The blue is the predictions. So the blue line being the model, and the blue data points being the prediction of this actual data point. So you can see here in this first one, we have output is equal to theta naught, or output is equal to a constant. And when you optimize this, you actually get the average of all of your outputs. And so it's just a straight line. It captures the trend very poorly. You can see here these red lines are your losses for each of these different data points. And from those, you can calculate the mean squared error. So if you square each of those lines and take the average, that is this mean squared error of how well does your model capture these data points. Now just adding one term, which is you want to add the thickness times theta 1, adding one more model parameter. You can see now we have a straight line capturing this trend. This is optimized model that we're showing here. And you can see how the loss is much better than what we had, without this term. You can see the mean squared error is probably a factor of 5 or 6 lower. Even the R squared, which is, again, R squared is just simply a measure of your prediction output versus the actual output. How well does it correlate with that? That went up quite a bit as well. So one way that you could approach this is let's add another input column. And in this new input column, we're going to have x1 squared. And we're going to add another model parameter, theta 2, multiplied by that. Now when we optimize this, we have a little bit of curvature in our data, and the mean squared error goes down once again. If you add another column, x1 cubed, and another model parameter, theta 3, you can see the mean squared error goes down once more. It captures all of these training data points, very well. It's really hard for a model to capture really the split in these data. So for the most part, it's doing a very good job. So this might lead you to think, and what I've shown down below is, this cost function is going down as we add these additional coefficients. So when you add x1 to the 4th, x1 to the 5th, x1 to the 6th and 7th, the mean squared error is continuing to go down as we add these additional terms. And essentially, we're increasing the complexity of our model. So you might think we just keep adding coefficients until the model has the best accuracy, right? And the response is, no, this results in what's known as overfitting. And we'll talk about that, here in the next set of slides. What is overfitting? What does it look like? And why is it a bad thing? Because clearly from this metric, which is designed to tell us how good the model is, it looks like adding more terms leads to a better model. So what is that trade-off? And here's just, a whole number of different models, and this is kind of getting at what happens as you overfit these. So again, this is your training data, and you can see how these different models tend to capture data here in the middle. Now, if we suddenly have a new data point that we want to make a prediction with our model, and it's in this middle regime, that would be a good data point for which of these models, is actually capturing the trend well. What you may also notice is there's some models that outside of these bounds, maybe conceptually, or you might have a thought about what it looks like outside of there. This is drastically increasing, drastically decreasing at the other side. In fact, you have this sort of aphysical behavior with one of the models, where as you decrease the thickness of the armor gets, almost, drastically stronger. So let's look at this. Here I've drawn 3 different columns. So we have an underfitting column, which is high bias, one that's a good fit, and one that's an overfitting with high variance. We're going to use regression is this row, and afterwards we're going to introduce a classification one as well. This degree up above, this is the degree of polynomial or the number of these terms that we've added to the model. The underlying function and that we've used here is actually, this is actually a cosine function where we've added noise. So the actual function underneath is a cosine function. It's gonna, fluctuate, and we want a model that's gonna capture that, a linear regression model. So with degree 1, you can look at the underfitting. What does that mean? It means our model isn't complex enough. We're trying to capture a curve with a straight line. And so this is an example. It's obviously not going to capture the trend of the data with a straight line. The good fit, this is actually pretty close to what the actual function looks like. So even though there's noise in these data points, this captures the underlying function fairly well. And then overfitting, again, you've got x to the 20th degree and everything up to that. And you can see how the model is trying to capture every single one of these points. It actually does a pretty decent job, but it's not reflecting the underlying relationship between x and y. So it's trying to capture all of the noise. And so this is an example of overfitting. And you can imagine that if you're trying to capture this underlying trend, it's doing a very poor job of that. For classification, what I started with was a random array of points, and then I actually chose a boundary line that's sort of a quarter circle in the upper right-hand corner. So I chose all these as one class, and everything outside of that boundary is another class. And then I added random noise to each of those points. And so after adding that random noise, you can see that some of them from the red class fall outside that boundary, some from the blue class fall inside the boundary. But essentially the boundary between the two classes is this semicircle. So this middle column, a good fit, second degree, again, this is logistic regression because it's classification, captures that very well. When you look at underfitting, so what does that look like for logistic regression and classification? Well, it's trying to capture a semicircle with a straight line. So that model is not complex enough to capture the underlying boundary. And then when you look at overfitting, this is fascinating to me, that logistic regression with an 8th degree polynomial, or, again, x to the 8th power and everything up to that, was actually able to kind of bend the boundary around these red points, in order to completely capture them and exclude all of the blue data. Or the blue class with that boundary. So it's fascinating that it, kind of fingers out or produces this wart-like feature to capture these points completely. But this is not the original boundary. So this little bit of noise, it's trying to capture all of the noise rather than capturing the actual trend or relationship between, these inputs in this case. Okay, so let's kind of go back to our original kind of conceptual plot. So what is the bias? Again, here's the data that we had from continually adding these these polynomial terms. So bias is the difference between the model prediction and the correct value that we are trying to predict. So, the loss and the cost function, this is essentially the bias of the model. And the variance is the variability of the model prediction, for a given data point. So it tells us around each data point, how much is the model varying? And again, a high variance model, you can look at it up here, is this overfit model, where it's fluctuating too much about the data points. And the optimal model is going to be somewhere in between. So what we're going to shoot for, and we'll talk about this with regularization, is we want a model that takes into account both the bias and the variance and this trade-off between them in order to come up with an optimal model that's going to make a good prediction on new data. So while we may train it and try to get, a model with low bias, we might want to evaluate that model, on new data. So test data to see how well that model generalizes. And this will give us a reflection of really the variance of the model. And there's different knobs. So when you think about how do we tell where we're at with the model, and how can we dial it back or push it forward so that we obtain this sort of optimal model point? One is with these hyperparameters. So again, remember, these hyperparameters are parameters that affect the training of the model. Model complexity, you've seen how by adding these additional terms, we changed a model from underfitting to overfitting. So certainly the model complexity can be one where you can, move a model along this, x-axis here. The number of features. So as you add more features, you give these models, more inputs to, come up with the more sophisticated relationship between inputs and outputs. And the last one here is regularization. And where this is really important, as we get into things like neural networks have so many parameters that it's very easy to overfit them. And so what regularization does is it allows you to take an overfit model and start to shift it back to the right so that you can shift it back to a model that does better at generalizing to new data. So here's kind of a question here. The best model, 1 has the lowest loss function. We've already shown that that isn't correct. 2 has low bias, high variance. 3 has low variance but high bias. 4 is like the medium-sized bear with the medium-sized voice, and Goldilocks is in the middle. And this should give it away if you haven't already, know the answer. You want your models to not be overfit, not be underfit. You want them in the middle. You want them to be optimal so that they make good predictions on new data. Aha. Okay, so we've come to the end of this. Just a very simple description of kind of variance versus bias trade-off with a few examples. And with that, well, yeah, thanks for hanging in there. Hopefully this talked a little bit and showed some examples of what we mean by underfit and overfit and variance versus bias trade-off for machine learning models. And next we're going to talk about really what is one of the best knobs, or one of the knobs that you can use to actually tune your model so that you try to hit kind of that optimal machine learning model. So with that, may the course be with you, and I'll see you in the next video.